Just keep it. Okay. I hope am I audible and visible? The screen is visible. I hope it is. Please let me know in the comment section. Uh, so as I told, today's topic is on Dirac Delta Function. Okay, and it is an important topic because you see there are many places in physics, that is like electromagnetic theory. Okay, like for example quantum mechanics, statistical mechanics, classical mechanics. In all these areas you'll find the applicability of Dirac Delta function. So you'll find invariably Dirac Delta function appearing in all these different aspects of physics. Okay, so before we embark on our journey of quantum mechanics, why not spend some time on Dirac Delta function? Okay, although there I have taught around 5 lectures on Dirac Delta function, and they are more rigorous and exhaustive. But today I'm going to sum it up in one lecture so that you get a gist of it. And once you are done with this lecture, I'll share you the 5 links in the description section where you can go and also learn about them in slightly greater detail. Dirac Delta function becomes quite indispensable when you have to find, let's say, point volume charge density of a point charge. So in electromagnetic theory, if you understand, if I want to write volume charge density of a point charge, how to go about it? Volume charge density of a point charge. So if I tell, give me what do you think about the volume charge density of a point charge? So how would you be able to explain it? See, as you know, if I am saying a point charge does not have any volume, not even infinitesimal small volume. Okay, not even infinitesimal small volume a point charge would have. Okay, so if I want to write, let's say rho, it will be dq upon dv, and I know that if my dv is as small as possible, because not even tending to 0, rather for point charge dv is equal to 0. So in your calculus, no such function exists. In calculus, no such function exists. Now, since there is a lack of such functions, so we need a different function to represent, let's say, a point charge density, as let's say volume charge density of a point charge. Okay. In other words, in other branches of physics, let us say in classical mechanics. In classical mechanics, it may occur in form of an impulse force. So let's say there is a force which acts exactly at some t equals to 0. Let's say ball hitting the back hitting the ball. So it is actually the impulsive kind of force. So impulsive forces, there you can have some force written in terms of as a function acting at just one point. Okay, so at just one point, at one time, at one point of time, the force would act. So to describe such impulsive force, you may again need Dirac Delta function. Okay, and also that it turns out that it also appears. This is something that I'm going to teach later on. It also appears in Green's function formalism. So basically, we are going to learn Green's function method of solving the boundary value problems. Okay, so there on the right hand side, we replace the forcing function by Dirac Delta function. This is something that we are going to do in the Green's function, and further. Okay, so if you are aware of Green's function, fine. If you are not aware of, don't worry. We are going to cover it in detail, and when we are going to cover it, I am going to show you that any differential equation which is satisfied by a Green's function, in those equation on the right hand side, we replace the forcing function Just remember it right now, whatever I'm saying, forcing function by Dirac delta function. We'll do it, don't worry. And this is an important part of your syllabus also. Okay, so you will also find them appearing in the wave equations as well. So there are different sources of applicability. Also in one of the theorems, Lively's theorem, indirectly or directly, in completeness criteria of wave function also you will see this appearing. Completeness criteria of wave function. So there are a lot. This is something that I remember right now. Otherwise, there are still many other applicative areas where you may find the usage of Dirac delta function. Now, without wasting a time, let us understand what does it represent. Okay, what does it represent? Okay. So a Dirac delta function. So let us take an example from Griffith. Let us take an example from Griffith because he has explained it in a nicer way. So what he says is, let us consider, he considers a vector field which is given by r cap upon r square. He considers a vector field r cap upon r square. And he says that what do you think about this particular vector field? So clearly this particular vector field is a positively oriented. You can see that r square always remain positive. So it is a positively oriented vector field. And since it is positive, so its divergence should be positive. Why its divergence should be positive? Because this is radially diverging outwards. So you can see r square is there. So initially your vector field I can make in this sense, then all the more small and then all the more small. So you can see that if I'm making 1 upon r square, I know its strength is going to weaken as r increases, but overall this is a radially diverging field, isn't it? Yes or no? Please let me know in your comment section. Is that understandable or should I repeat it? So basically, if I'm going to make just an idea of the vector field, then vector field would be this way, right? I hope it is understandable. Please let me know in the comment section if you are not getting it. Okay, so this is how this vector field would be. So it will be pointing outwards, and with increase in r, its strength would decrease. So therefore, I'm making smaller arrows as I'm progressing. So overall, you can see that this is how. So this particular vector field must be positive, and this must be diverging outwards. So what you can expect? What is divergence? Divergence is how well your vector field diverges. So clearly you can expect that del dot v vector should be at least positive. Okay, should be positive. This is what you can expect. This is what you can expect. That's okay. So okay. See r cap upon r square. Okay. See what is r cap? R cap points in the direction of, it points in the direction of, increasing direction of r, right? So r cap points in the increasing direction of increasing r, right? And what is 1 upon r square? 1 upon r square would be positive. Obviously 1 upon r square, with increasing r, the strength would decrease. So what I have done, when I'm picturizing it using the vector fields, like diagrammatically, what I'm doing, initially I'm making a stronger like longer length of this, and then I'm showing it with smaller length. So basically what does it mean? It means that its strength is obviously getting diminished as r increases. As r increases, you also understand that as r tends to infinity, 1 upon r square would go to 0. So as r increases, and what is r? You should understand that r is nothing but it is equal to root over x square plus y square plus z square. So if you are going to move further away from the origin, the strength of the field would decrease, but overall it would be pointing outwards only. It would be pointing outwards. So what is the divergence that you can expect out of this? Clearly, one can say that the divergence should be positive, because what is the physical meaning of divergence? The physical meaning of divergence is how well your vector field is diverging. How well your vector field is diverging. Yes or no? Now let me know if that's not something that you don't get it. How well your vector field diverges. Is that understandable, Harish? Yes or no? Okay, so I hope it is understandable. If it's not, please let me know, and then I shall begin again. Okay, so now what happens is, uh, this is what we can expect. Okay, now instead I apply a formula. I apply the formula of divergence. I apply the formula of divergence. So what is divergence formula for radial? If I want to just write the radial part, it is 1 upon r square del by del r of r square into this particular 1 upon r square, because here you have only radial field. So this will be equals to 1 upon r square del by del r of 1. And what is del by del r of 1? 0. Now this is quite intriguing, because see, you were expecting that divergence of vector field should be positive. However, you get the divergence of vector field to be 0. Now, there is a contradiction here. Why there is a contradiction? Because you can see clearly from the diagram itself that you can expect the divergence to be positive. However, you are getting the divergence to be 0. Nor this is wrong, nor this is wrong. It implies there lies certain ambiguity in conceptualizing what we have done. So where lies the ambiguity? So in order to find the ambiguity, what I'm going to do, I'm going to just enclose this particular thing. Okay, just let me help myself with a little bit of things. Okay. So let me enclose this stuff in a, let's say, a sphere. Let me enclose it in sphere. Okay, let me enclose it in a sphere of radius capital R. Let us say this sphere is of radius capital R. If I want to find a volume integral del dot v vector d tau over this particular sphere, let us say S, what will I get over the volume of, let's say, this particular sphere S has a volume V, and if I want to find this particular integral, this would be 0. However, if I want to find v vector dot dA and over the surface, closed surface, spherical surface, then what I'll get? I know what is my this thing. This is 1 upon r square, r cap. On the surface of the sphere, if you make the ds vector, I hope this is something that you know. If you don't know, just remember it. The differential area element on the surface of the sphere is given by r square sine theta d phi. Okay, so here I will get dot r square sine theta d phi, and here you can say that, let's say, r is equal to capital R, because the radius I have taken capital R. So what I'll get, this r gets cancelled, and here you have again r cap, because this points in r cap direction only. So overall, this is sine theta d phi. What it is? It is equals to 4 pi, because on the complete sphere, sine theta integral goes from 0 to pi, and cos theta, phi integration goes from 0 to 2 pi. So this is for the full sphere. The limits for theta and phi are pi and 2 pi respectively. And what has happened? If I find v vector dot dA, that is, if I want to find the flux of the vector field through the surface S, which is nothing but the spherical surface S, then this comes out to be 4 pi. However, if I am evaluating the volume integral comes out to be 0. Now again there is a discrepancy, because you know from the Gauss divergence theorem that these two integrals are equal. So now there arises a question that where does the discrepancy lie? Anybody is going to ask us that where does the discrepancy lie? So where does the discrepancy lie? Where does the discrepancy lie? So obviously one has to think about it. So clearly, what has happened at the very first instance, when I was using this formula d by dr of 1 upon r square, at that very instant I have, because this is an operator, this works only in the regime where it is it is meant to operate. So clearly R not equal to 0 is that regime where you can use this particular thing. Okay, so whenever I am applying this del dot v vector, del dot v vector, del dot v vector, I am actually avoiding, there is an avoidance of the singular point r equal to 0, and this is due to the mathematics itself. So there is an avoidance of this singular point r equal to 0. Since we are avoiding it, so therefore we are not including it in our definition. However, when we were evaluating this surface integral, this r equal to 0 was coming inside. R equal to 0 was coming inside, and we can find that the flux through this particular surface, spherical surface of radius r, we were getting it to be equal to 4 pi. However, when we were finding the volume integral using del dot v vector d tau, this particular integral was coming out to be 0. That implies while evaluating this, we are not incorporating the singular point, that is r equal to 0. So this is not there. However, when we are finding this this particular surface integral, then this point 4 pi comes. This implies that this 4 pi contribution is entirely coming from the center point. That is, this particular point, this particular center point's contribution to this surface integral is 4 pi. So this is very much clear that this 4 pi contribution comes from the center point, that is the point of the singularity. I hope till now everything is clear. If there is a lack of clarity, please let me know. Okay, so therefore it happens so that whatever 4 pi contribution is coming in this surface integral, it must come from this particular point only. Otherwise, how would you expect this 4 pi? Because see, there is nothing wrong with this vector calculus. These are well established theorems, they are well proven. So we cannot say that this theorem becomes wrong at certain cases. No, that's not the case. That's not the case. So this 4 pi contribution is certainly coming from the origin. There is no other way out, because see, del dot v vector, we are getting 0. That is not wrong, but we are getting it for all r not equal to 0. That implies if I am trying to find this del dot v vector d tau, this integral, it implies for all this region where r is not equal to 0, the contribution would be 0 only. So from here, if you want to evaluate del dot v vector, you will get 0. But certainly at center, there should be something. There should be something that you are not able to evaluate from your ordinary calculus. I'm not saying that calculus is ordinary. I'm just trying to say the functions of variable 1 that you study from your standard 12th, where teacher says what is the domain of the function 1 over x. So you instantly say that x equal to 0. So sorry. So I know that from my standard 12th calculus that okay, I cannot define a function which is 1 over 0. But I certainly need some function here. I certainly need something to describe. So here in mathematics we have certain functions, and these are actually not functions, these are generalized function. However, if you want to get into the theory of generalized function, it will take you a lot amount of time. A book I can recommend, the book is called as I'll let you know. Book actually I just forgot. Okay, so there is a book in advanced physics, advanced mathematics only. That is a good book in which this treatment of generalized function is given. So I'll let you know. Don't worry. I hope everything is clear. Harish has not come with any. Please let me know, Harish, if that's clear. So should I move ahead then? Okay, so if everybody is getting it, so let us move ahead. Okay, so it implies that whatever contribution is coming, it is coming from the center. So in order to justify this particular thing, we come up with a solution called as Dirac Delta Function. And I'll come to this problem all over again, but now let us first define what is Dirac Delta Function, then we'll come back to this problem all over again, don't worry. Okay, so let us first define one-dimensional Dirac Delta Function. All of this thing is given in Griffith, so there's nothing new that I'm teaching, okay? But just that you should, because Griffith offers you a certain sense of physical understanding. Otherwise, any mathematical physics book you take, they will start with this particular thing. One-dimensional Dirac Delta function. Okay. So what is one-dimensional Dirac Delta function? So if I am saying that Dirac Delta function is defined at x equal to 0, it implies the entire contribution is coming from the center. Let us say that my point charge is placed here. If my point charge is placed here, the entire volume charge contribution is going to come from this particular point only. Okay, let's say this is origin. And this contribution is infinitely large. This is infinite. And this is 0. So this is how you define your one-dimensional Dirac Delta function. The Dirac Delta function Dirac x is given by is equals to infinite if x equal to 0, and it is equal to 0 if x is not equal to 0. Now you will be in a fix that how to understand this, because now here you are in fix how to think about it. So just understand that it is so designed that the area under the spike should be unity. Area under this spike must be unity. Area under the spike must be unity. So if area under the spike is this is unity, it implies whether I integrate from minus infinity to plus infinity, because for all other points except 0, this is already 0. So whatever this integration would come, this would actually account for the area under this narrow peak, and this is equals to 1. So this is how you define your Dirac Delta function. These two things together define your Dirac Delta function. In general, in literature, it is called as the generalized function. And we actually, why it is called? Because we actually understand it as the limiting case of sequence of functions. Limiting case of sequence of function. This is something that I have discussed in greater detail in 5 of those lectures which I was mentioning in the initial part of my lecture. So I'll give you those lectures in the description. Don't worry, just go through this and you will be able to understand what I mean by when I say that limiting case of sequence of function, because then it will take a lot more time. We have to start quantum mechanics in around with some mathematical you can say background right now. So that is why I'm giving you background. Let's say I'll give you some background of vector spaces. I'll give you some background of operators. I'll give you some background of matrices. After that, the quantum mechanics will become easier for you. That is why all these things are I'm doing. So okay, for just now, just understand that these are generalized function, or at times in statistical terminology, you can say that entire distribution is here. Okay. Usually what happens, let's say if I say that my charge is distributed uniformly in the volume, so you can visualize this way. But how to understand the distribution of a point charge? So for that mathematical rescue is to define it using Dirac Delta function. So Dirac Delta function in statistical terminologies are also called as the in statistics, or you can say statistically we can say that they are nothing but they are distributions also. Okay, so these two terms you should remember. Now, there is one important property of Dirac Delta function, which is this. Okay, which is this. So, for example, let us say that some continuous function is here. So, let us say some continuous function is here. And if I multiply it with Dirac Delta function, Dirac of x. So, I know that for all x not equal to 0, it is obviously 0. And only at x equal to 0, there is some sense. Obviously, this will be infinitely large, but there is some sense. So for all x not equal to 0, this will be 0. But at x equal to 0, there may be some sense. So what happens is, if I want to integrate minus infinity to plus infinity function f of x, Dirac of x dx, then this is equals to what? Then this is equals to f of 0. Because see, only at x equal to 0, this will be something. And at x equal to 0, x would become f0. It goes out of integral, and this integration becomes 1 because area under the spike is simply 1. Okay, so I know that at x equal to 0, this f of 0 would become constant. It goes out of the frame, and this particular integration, that is at x equal to 0, what does it imply? It implies area under the spike, and area under the spike is what? It is equal to 1. So you actually get only f of 0. Similarly, if you want to generalize this property, then you can generalize in this fashion. You can write minus infinity to plus infinity, minus infinity to plus infinity, f of x Dirac of x minus of a d of x, and you can write it as f of a. So what you have to do whenever you've got this kind of thing, what one needs to see is just see where this argument becomes 0. At which place this argument becomes 0? It becomes 0 at x equal to a. Just place that argument inside function. This becomes your answer. And this is one of the most exploited properties in exams. So you can see in exams, most of the questions come from this particular domain only. So let us do some questions also so that you are able to understand what I want to teach. So for example, I'm just giving you a minute. Please write in the comment section the answer for the following. Just give me an answer for 0 to 3 x cube Dirac of x minus 2 dx. Just let me know what will the answer. I think this is easy. You'll be able to do it. Please let me know the answer for this. I think this is easy. If it's not easy, then I'll do it for you. But just take 2 minutes and just try to solve it. Okay, 8, good. So this is 8 because simply you have to just see where this argument becomes 0. This argument becomes 0 at x equal to 2. Just place this x equal to 2 here. This answer would be 8. I think this is quite easy. So, okay. Now, moving further, always understand whenever you have to find some property, whenever you have to find some property relevant to, whenever you have to find some property relevant to Dirac Delta function, what do? You just use integration. Use integration. What do I want to say? Let us say I have one statement which says d1. There is one statement d1x which involves Dirac delta function, and there is another statement d2x which involves Dirac delta function, and I want to actually know the relation between them. So what I have to do? I have to do just one thing, and that is I have to multiply it with some suitable function, and I have to integrate them out. So for example, if I want to derive the scaling property, I'm not going to derive any property from here on, but just I'm saying how to go about it. So if I want to write this Dirac of kx, this is equals to 1 upon mod of k Dirac of x. How to understand this? So see how to understand this. Okay, so if I want to do this, so there is one statement which involves this. There is one statement which involves this. So what I'll do, I'll simply take a legitimate test function. So let me take a legitimate continuous test function. Continuous test function. Legitimate means which is integrable, right? So which you can integrate somehow. So if I integrate this particular stuff from minus infinity to plus infinity, what will happen? Let us see. So what I will do, if I'm integrating it from minus infinity to plus infinity, so I'll use one thing. I'll use this. I'll take this. I'm writing here. Okay. So I'll do one thing. I'll write let kx be equals to y. Let kx be equals to y. And right now I'm taking k to be positive. Right now I'm taking k to be positive. So dx would become 1 upon k dy. Dx would become 1 upon k dy. When dx would become 1 upon k dy, so this integration would remain from c. This was defined on x, so x was going towards minus infinity. So if x is going towards minus infinity into k, so y limit also would remain minus infinity only, and y upper limit will also remain plus infinity only. And this would be simply f of y upon k, and this will be Dirac of y, and there would be, I think, dy by k. Okay, this is only if k is positive. This is only if k is positive. So answer that you must be getting is 1 upon k integration minus infinity to plus infinity Dirac of y, and then you have this f of y by k dy, and what you will get out of this, you will get simply f of 0. So this is f of 0 divided by k. Okay. Similarly, if I have this, similarly if k is negative, what will happen? If k is negative, this lower limit will become infinity, upper limit will become minus infinity, and all those things will remain the same. Fy upon k will remain fy upon k, Dirac of y would remain Dirac of y, dy would remain dy, k would remain k, and so you will get a negative sign from minus infinity to plus infinity. F of y upon k, Dirac of y, 1 upon k, 1 upon k would come out, minus 1 upon k would come out, and there is dy. So this integration would also become f of 0. So when k is negative, this integration is accompanied by minus 1 upon k f of 0. Okay, so now I'm going to write this thing in summarizingly. I can say that minus infinity to plus infinity, f of x Dirac of kx dx is equals to what? Is equals to, and what is this? Basically what I have to see, what I have to write, what I'll write it is equals to 1 upon k f of 0 if k is positive, and it is equal to 1 upon minus k f of 0 if k is negative. Yesterday only I taught you that if I want to write mod of k would be equal to k if k is greater than 0, and it is equals to minus k if k is less than 0. So clearly, summarizingly, I can write this in one step, and that one step is minus infinity to plus infinity f of x Dirac kx dx is nothing but it is equal to 1 upon modulus of k and f of 0. So if I want to write f of 0, I'll write it from minus infinity to plus infinity f of x Dirac of x dx. And if I take this mod of k inside, from the comparison, I can just write minus infinity to plus infinity f of x Dirac kx dx is equals to minus infinity to plus infinity f of x Dirac of x upon modulus of k dx. So you compare these two things and you can write that Dirac of kx is equals to 1 upon modulus of k Dirac of x. So this is at times referred to as the scaling property. The first property that I taught you was called as is usually called as filtering property. So I hope it is clear. Please let me know if there is a problem anywhere. Okay, should I move ahead? Okay, should I go ahead? Yes, okay. So this is how it is. So now let us move to another important property, which again is being utilized mostly in the examination, and that is instead of a Dirac delta function, if function of a Dirac delta function itself is given. So basically, instead of Dirac delta function, if Dirac delta function appears to be in some appears as an argument of some function. So I will not derive this. I have derived this in the detailed lectures that I have already given. So just remember that, let's say, if instead of if instead of x the function itself appears as an argument. So if instead of what I was saying argument of right. So I was saying that if function itself appears as an argument of Dirac delta function. So till now you were doing Dirac of x. Now I'm saying, if I am saying that instead of Dirac x, I'm saying Dirac of g of x, then what to do? It is equivalent to summation I Dirac of x minus ai divided by modulus of g dash ai. Here remember, ai's are simple zeros. They are not repeated zeros. So let's say if I'm saying what would be Dirac of x minus a ka whole square, so you'll say it does not make sense because this is not defined. It does not make sense because here you have repeated zeros. Here you have repeated 0. So this formula that I'm stating is only valid if g of x has simple zeros, not repeated zeros. Okay, so simple 0 means which do not have multiplicity. So let us say if I'm talking of, let's say I'm talking of, let us take one example and then do it. So one of the examples from exam only let me take, and that will actually help you understand this particular concept. So remember, the word of caution that I'm giving to you is that this formula is not valid for repeated zeros. Like here, AIs cannot be repeated zeros. They have to be what? They have to be simple zeros. Okay, they cannot be repeated zeros. Just let me help myself with this problem, and then I'll give you this particular problem. So let us do one question here. This particular question was asked in JEST examination. Okay, the question says find the integration minus infinity to plus infinity dx Dirac of x square minus pi square cosine of x. Okay, we have to do this particular integration. How to do this integration? So, as I told you, Dirac of x square minus pi square, what it will be equals to? Clearly, there are two roots, x equals to plus minus pi, and both are individual roots. Okay, and both have multiplicity 1. So you can actually factorize and understand that there is a multiplicity of 1. So x equals to 1, x equal to pi, and x equal to minus pi. These two are the zeros. Okay. So if I want to find what is this, then I can write simply Dirac of x minus pi, because see what was given to you. It was given that Dirac of g of x. I'm just writing the formula all over again. If you are Dirac of x minus of ai, and then you were dividing it by modulus of g dash ai. So the derivative here would refer to 2x divided by modulus of. Since modulus is there, whether you divide it, whether you write 2 into minus pi or whether you write 2 into plus of pi, they are one and the same thing. So basically it is 2x, and simply I'll write 2 pi. I hope it is clear. If it's not clear, I'll again do it for you. So basically what does it mean? Let me do it in detail so that at first things should be in detail, otherwise you'll not be able to follow it. Okay, so let me just write it here. So if I'm writing Dirac of x square minus pi square, what does it mean? It means I'm writing first a1 would be Dirac, let's say x minus of pi divided by g dash. What would be g dash? 2x at x equal to pi, plus Dirac of x plus pi, and here divided by 2x at x equals to minus pi. So if you replace this up, so what you'll get? You'll get Dirac of x minus pi divided by 2 pi plus Dirac of x plus pi divided by 2 pi. I hope it is clear now. Okay, good. So that implies these two are equivalent. So now I'll use this thing and then we'll do the problem. So what does the problem say? Problem say integrate from minus infinity to plus infinity cosine of x, and here you have Dirac of x minus pi plus Dirac of x plus pi, and then you have this 1 upon 2 pi I'm taking outside, and you have this d of x. So what do you get? Cos, the first term you will get, what is cos of pi? Cos of pi is minus 1, and again this cos of minus pi. So this will be, I think I will write once, this is cos of pi, then you will get cos of minus pi. Cos of minus pi is also minus 1, cos of pi is also minus 1. The answer should come out as minus 1 upon pi. I hope it is clear. I hope it is clear. Okay, so this is quite clear. So I don't need to put more stress here. Okay. Now let us do another problem related to this only, and this is again asked in JEST exam only. So much of these problems I have done, but I think the best way of revising this topic is through problems only, so that you are able to understand. Now again I'm doing another problem. This is again asked in JEST. JEST, the question asks you find minus infinity to plus infinity exponential of minus of modulus of x Dirac of sine pi x dx. How to do this? Okay, so how to go about it? Let us see. Let us first understand this particular structure. So structure says Dirac of sine of pi x. So I told you Dirac delta function, whenever you have to investigate, just see where this argument becomes 0. This argument becomes 0, sine pi x becomes 0 only when pi x becomes equals to n pi, where n belongs to integers. So this will be like this cancels. It implies x is equals to n, where n belongs to integers. So what can be x? X can be equal to 0, plus minus 1, plus minus 2, plus minus 3, so on and so forth. And all these are simple zeros. All these are simple zeros. Now let us find an answer for it. So pi minus infinity to plus infinity, this is exponential minus of modulus, and then instead of this sine pi x, what I'll write? I'll write simply Dirac of x plus Dirac of x minus 1, Dirac of x plus 1, then plus Dirac of x minus 2, then plus Dirac of x plus 2, dash 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 dash, so on and so forth. And let us find the derivative also. So basically, what is the derivative of sine? The derivative of sine is simply pi cos pi x modulus. This is something that we'll have to write in the denominator side at x equals to n. So what it will be equals to? It will be equals to pi cos n pi modulus. Always remember, cos n pi is equals to minus 1 raised to power n. Because if it is odd, the answer would be minus 1. If it is even, the answer would be 1. So in any case, this mod cos pi n would become 1. So you'll have only pi divided by entirely this. So if I divide it by pi, this pi and this pi gets cancelled. Is that clear? Or should I explain it all over again? Please let me know. Is that clear, or should I repeat it? See, what I was telling is, if I have to write this particular entire structure, sine pi x, this is absolutely fine. I'm writing it Dirac of x minus n, where n belongs to integer, but I have to divide it also now. So I'll divide it by pi cos pi x, and all these things I have to evaluate at x equals to n. So if I'm using x equal to n, cos n pi is minus 1 raised to power n, modulus of it will give me 1, and pi is here. So this pi and this pi gets cancelled. Now I'm left with this. Okay, now let us do. If I'm doing the first, this will be 1 plus x equals to 1. So place x equal to 1 here. So you'll get e to power exponential minus 1. Put x equals to minus 1. If you place x equal to minus 1 mod is again 1. So again negative. Then plus exponential minus 2 plus exponential minus 2 dash 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 dash. So all these things will add up, and you will get what? You will get 1 plus 1 upon e plus 1 upon e square plus, sorry, this is 2, this is 2. Then you will have 2 upon e cube, so on and so forth. Is that clear? Because these two will become 2 by e, these two will become 2 by e square, and so on and so forth. I hope it is clear. And I know, and this is a sum of geometric, this is simply a geometric progression. So instead of this, I'm going to write it is 1 plus, this is a geometric progression, isn't it? So from here, if you see, this is a geometric progression with common ratio 1 upon e. And what is 1 upon e? 1 upon e is less than 1. Because 1 upon e is what? 1 upon e is 0.368. Or yesterday only I told you, whenever you have a geometric progression, just see the common ratio should be less than 1. If it is the case, then this is a convergent series. So I'll take a 2 common out, and here you will have a upon 1 minus of sorry, A. So if I consider this as A, A upon 1 minus of R. What is R? 1 upon E. Is that clear? So overall, this will become 1 plus 2 upon E minus 1 added up. So you'll get E plus 1 divided by E minus 1. I hope it is clear. Please let me know if that's clear. So I will move ahead then. Otherwise, I'll stop here and again answer your question. So I just need your nod as to whether I should move ahead or should I not move ahead and wait for a minute. So I'm waiting for a minute. Please let me know in the comment section if that's fine. Okay. Please let me know in the comment section. Is that fine? Okay. So I think it is clear. Okay. So okay. So this is what I had to say. Now there are at times a thought that comes into mind regards the dimension of the Dirac delta function. There are times where you think about what should be the dimension of the Dirac delta function. What should be the dimension of the Dirac delta function? So if you think about it, just think about this particular thing. Just think about the I should say, what should I say? Just think about the filtering property that I suggested. So just think about the filtering property that I suggested. So what is the filtering property? I told you, if I integrate from minus infinity to plus infinity, Dirac of x, f of x, d f of x, it is equivalent to what? It is equal to, let's say, f of 0. Okay. Now, if at all these two are equal, then the dimension here and dimension here must be equivalent. They must. So it implies what? It implies dimension here and dimension must be equal. And I know that whether it is f of 0 or whether I write f of x, both should have the same dimension. Okay, both must have the same dimension. And see, this is constant. This is constant. It implies what? It implies Dirac of x into d of x. This particular thing must be dimensionless. And if this particular thing is dimensionless, then what does it imply? It implies that Dirac x dimension should be equal to dimension of 1 upon dimension of this d of x, or simply you can say Dirac of x dimension must be equal to 1 upon the dimension of x. 1 upon dimension of x. Is that clear? See, f of 0 must be a constant, right? So f of 0 must be a constant. If it is a constant here, so this must also yield me a constant. After all, this and this dimension should be same. This and this dimension should be same. It implies Dirac of x dx, this particular thing should be dimensionless. If this is dimensionless, then if let's say this is of dimension of length, so this should be dimension of length inverse. Let us say this is dimension of momentum, so this should be a dimension of momentum inverse. Is that clear? So always remember that whatever argument comes inside, so I'm writing the dimension, I'm writing dimension of Dirac delta function is equals to the inverse dimension of the argument, and it has been asked in JEST exam only. So for JEST and TFR, this is a very like for NET also, NET, JEST and TFR, not JAM and other examination, because there it's not that much asked. But you see, you have to understand this is not that easy thing. I'll let you know with the problem also. So dimension of Dirac delta function is the inverse dimension of the argument. What is argument? This argument I'm saying. So for example, if you are saying that this argument x has dimension of length, then the dimension of this entire Dirac delta function will be inverse of length. If this Dirac delta function is having this particular argument is having the dimension of momentum, then this particular Dirac delta function will be having the dimension of inverse of momentum. So this is something that you should remember. I hope this is clear. I mean, this is all basic properties that I'm listing right now. Okay, so this is one of the most exploited properties, at least by jest. So I don't think now they're going to ask from this particular dimension, but even if in case they ask, I think this is an important thing that you should remember. And right now what we are doing some mathematical preliminaries before we can start quantum mechanics. Okay, because see, I was initially thinking that I should start directly quantum mechanics, but then I thought if I'm not covering all these basic things, then there would be a problem. And once we cover all these basic things, then quantum mechanics will not remain a problem, because it is slightly easier subject than classical physics. In classical physics, you should have a physical intuition. If you don't have physical intuition, then you may make mistakes. But here there is no such problem, because already this is so counterintuitive that whatever mathematics is yielding you, you have to accept it. You have to accept it. And see, the world is running over quantum mechanical phenomena, isn't it? Superconductivity, we all know. It is a quantum mechanical phenomenon. Magnetism, again, it is a quantum mechanical formulation. So basically, your entire day you are working in magnetism. Because why I am so elaborating in magnetism? Because I belong to magnetic community. But in general, understand, without quantum mechanics, you cannot run magnetism, right? After all, the basic unit for magnetism is what? Spins. And spins has got no classical analog. Okay, so no. Why I'm saying quantum mechanics is way easier? Because it is a postulatory theory. There are postulates to it. You have to accept it, and you can see that all your experimentations are working accordingly. So you cannot actually say that this is wrong. Although there are physicists and mathematicians who work on the mathematical structure of quantum mechanics. That is a different aspect altogether. So they actually work in this particular domain, like quantum information computation, or you can say mathematical understanding or mathematical development of this quantum mechanics also remains to be a big research subject in itself. But because we are MSc students, for us they have made our life simple by giving us some postulates that these are the postulates that you have to adhere to. But before coming to the postulate, why not actually spend some time understanding some mathematical preliminaries around it? So if you understand all those things, then life would be easy. This is what is my suggestion to you. Okay, so I think this is these are 4 to 5 properties that I have listed. Now let us move a few more and do a few more questions. I hope these are clear to you. Okay, chalo. So let us move ahead. This dimension thing is clear, and please be, on chat just remain slightly, you can say, reciprocative, so that I will be able to understand that you are getting it or not getting it. Okay, now what happens in, let us say we have to, without proof I'm writing it, all these things I have done in detail in classes, so you can see those things. So if I was still now writing Dirac delta function in one dimension. I was still now writing Dirac delta function in one dimension. Now what would be Dirac delta function in 3 dimensions? What would be Dirac delta function in 3 dimensions? For this, let us again come back to the problem that we started from. We said that we were defining a vector field 1 upon r square, right? We were defining a vector field 1 upon r square, right? So we were defining a vector field 1 upon r square, and del dot v vector was coming out to be equals to what? It was coming out to be equal to 0 if r is not equal to 0, and otherwise this surface integral v dot dA was coming out to be equals to 4 pi. What does it imply? It implies that if I include r equal to 0 into my definition, then del dot v vector should give me a 4 pi. But now I have to rectify my definition. But now I have to rectify my definition. So how to rectify my definition? What I will do, I will actually use something called as three-dimensional Dirac Delta function. In order to rectify my definition, what I'm going to use, I'm going to use my three-dimensional Dirac Delta function. I'm going to use three-dimensional Dirac Delta function. So what I will do, so the problem was this only. So del dot v vector should give me 4 pi, and this 4 pi should come from, this should come from origin, because for all other points del dot v vector is 0. So at r equal to 0, this 4 pi contribution should come from there. Only in that case we can say that this theorem is valid. Obviously this theorem is valid. I mean, there is no exception to Gauss divergence theorem. Okay, there is no exception to Gauss. So basically, if both of them are equal, then it should happen that del dot v vector should be equal to what? Because this is something that you are getting as 4 pi. So if you are getting this right hand side as 4 pi, so left hand side should be 4 pi. And you know that for all r not equal to 0, del dot v vector is already 0. So it implies whatever contribution is coming, it is coming from the center, and that is equal to 4 of pi. So it implies del dot v vector should be 4 pi from origin. Now, how to write this from origin every time? So what I'll do, I'll write something called as three-dimensional Dirac Delta function by writing it as Dirac of R. So whatever contribution is coming, it is coming from the center. Now, if it is that the case, then I know that del dot v vector d tau integration should be equal to what? It should be integration Dirac R d tau. Now this should be equals to unity. So this is corresponding. This is having analogous. This is analogous to your one-dimensional result, because in one dimension we had integration Dirac of x dx should be equal to 1. In 3 dimension, Dirac cube r d tau should be equal to 1. Now if this is 1, you are getting 4 pi, and you have rectified the problem. So always remember, this is one of the most important result that you should remember, one of the most intriguing result that you should remember, and this is one of the most exploited areas of physics, at least competitive wise. So many times questions have been asked from this particular concept. Please remember, del dot r cap upon r square is always equals to 4 pi Dirac cube of r. So this is how you write your Dirac delta function in radial coordinates. So if you want to write in simply Cartesian, then it's absolutely fine. You can write that del r cube is simply equals to what? Del x into del y into del z. Okay. If you want to write the same, in what I can say, if you want to write the same in other coordinate systems, let us say if I want to write Dirac cube r vector minus, let us say r vector dash, and this I want to write in cylindrical coordinates. If I want to write in cylindrical coordinates, only one caution that I am going to give you: just divide it by the scale. If you have what I say, if you have been through your MSc first sem, you know that there are some functions like these in orthogonal curvilinear coordinates. So you have to divide it by scale. So 1 over rho, Dirac of rho minus rho dash, Dirac of what should I take? Phi minus phi dash, and then Dirac of z minus z dash. Similarly, in 3 dimensions, if I want to write spherical polar coordinates, then this particular thing will become 1 upon simply r square sine theta, Dirac of r minus r dash, Dirac of theta minus theta dash, and Dirac of phi minus phi dash. Okay, so this is a prescription that I am giving to you. Without proof I am writing. All these things you should remember. This is the formulation of 3-dimensional Dirac delta function. This is how you write it. Is that clear? Okay, I hope this is clear to you, and if that's clear, then I'll move ahead. Okay, just give me one answer. Okay. So what I'm writing Dirac of sine of x minus cosine of x equivalent to summation n Cn Dirac of x minus of xn. Okay, I'm writing this way. Now I'm asking what would be Cn and what would be Xn. What would be Cn and what would be Xn. So what I'm doing, I'm actually writing this as the sum of, so sorry, I'm writing this as sum of Dirac functions. So I'm writing this as sum of Dirac functions. And now I'm asking you, if I'm writing it in form of sum of Dirac function, then what would be this amplitude, like constant, like Cn, and what would be this argument Xn? What do you think this would be? Okay, chalo, let me help you in this. See, I told you that whenever you have, instead of function itself, you have this argument inside as a function. So argument happens to be a function, then what happens? Then just find where this is 0. So sin x is equal to cosine x. When it happens so sin x happens to be cosine x only if tan x is equal to 1. And when tan x equals to 1, it happens to be at n pi, it happens to be at pi by 4. And then because of the periodicity, then general solution you can write n pi plus pi by 4. I think this is quite clear from your trigonometry classes, that this is the general solution for tan x equal to 1. Okay, now what I would do, I would simply say that Dirac of sin x minus cosine x is equals to Dirac of x minus of n pi plus pi by 4 divided by, here n should belongs to z, divided by modulus of the derivative of sin x is cosine x, and the derivative of cosine x is minus of sin x, so plus sin of x, at x equals to n pi plus pi by 4. And remember, sin pi by 4 is also 1 by root 2, and cos pi by 4 is also 1 by root 2. Is that clear? You have to divide it by the derivative now. So if I divide it by derivative, the sin x derivative is cosine x, and cosine x derivative is simply sin of x. I hope it is clear. Or you can take, if you want, you can take this sin x also common out. So if you want to take that also, that is also fine. So this will give you n belongs to z. There would be Dirac of x minus of n pi plus pi by 4 divided by modulus of sin x, or you can take modulus of cosine x outside. Inside you have this 1 plus tangent x, and you know that already this is what, this is 1. This would be 1 upon root 2. This would be 1 upon root 2. This would be simply 2. So you will get what? You will get 1 upon root 2 here. Is that clear? This would be 1 upon root 2, right? And this is 2. So this gets cancelled. You will get root 2. So your Cn's would be 1 upon root 2, and your Xn would be simply n pi plus pi by 4. Is that clear or not clear? Okay, so I hope it is clear. If it's not clear, please let me know. Because see, in the first quadrant, cos is positive, sin is positive. Both will give me 1 by root 2 plus 1 by root 2, which is simply root over 2. And in the third quadrant, both are negative, minus 1 upon root 2, minus 1 upon root 2. So answer would be, I think, 1 upon root 2 here. I hope it is clear. And xn would be simply. Okay, now let us do a few more questions. Because only if you are exposed to much of the questions, then you can do good in exam. Okay, and this is how, because exam approach should be this way only. Understand the theory. If you are not able to get into the derivation part, let it be for the, because ultimate goal right now is your exam, right? So even if you are not able to understand the complete derivation part, let it be. Let it be. first understand that particular concept, try to apply those concepts to your problems that are asked in the examination, because only then you will be able to understand the demand of the exam. And once you know the demand of the exam, you work out there, and whenever you are preparing for interview, go back to your drawing board, try to formulate that particular derivation all over again, and it will come somehow. Oh, it will come somehow, don't worry. So, okay, so now having said all these things, always remember, let us say I am saying that my point charge q is placed at coordinate x naught comma y naught comma z. Let us say that my point charge is placed at point x naught comma y naught comma z naught. Let us say that my point charge x naught is placed at point x naught comma y naught comma z naught. Then how to write the point charge density? So point charge density rho as a function of r can be written as q times Dirac of x minus x naught, Dirac of y minus y naught, and Dirac of z minus z. So if you find this, like in this fashion, if something has been written, it implies you are talking about a point charge q placed at x naught comma y naught comma z naught. It talks about point charge placed at point x naught comma y naught comma z. Okay, I hope it is clear. Okay, another important property that you should remember is that symmetry of Dirac delta function. Always remember that Dirac delta function is a symmetric function. That is, if I want to find Dirac of x, or whether I write Dirac of minus x, they mean one and the same thing. Whether I write Dirac of x minus a, or whether I write Dirac of x minus a minus x, they are one and the same thing. Clearly you can see, because effectively what you need to find, you just need to find where it is 0. So whether you write x equal to 0 or minus x equal to 0, one and the same thing. Here also, whether you write x minus a equal to 0 or a minus x equal to 0, one and the same thing. So always remember that Dirac delta function is symmetric. Although this is something that I have just taught you somehow. Although when you see those lectures which I have recorded, which I have taught in the previous session, you will see that I have demonstrated Dirac delta function as sequence of some, as limiting case of sequence of some functions. So there you will be able to understand the pure sense of saying Dirac delta function to be symmetric. Right now, just understand this. Just remember this thing. Just remember this particular thing. Now, a word of caution for your exam. So, few days back, a student asked me a question. I think it was in some sheet or somewhere. He said that the electric field was given to him in this form, k r square r cap, and it was asked, find the charge contained in the sphere of radius capital R. Question that was asked was find the charge contained in the sphere of radius R. This is what was the question. I hope a little bit of Gauss law you all know. If you know Gauss law, I'll straightway use it, and if you don't know, then I'll produce it. So for example, if such questions come in the exam, the best strategy, if they're asking charge, don't try to find del dot v vector, del dot e vector. If you find del dot e vector and then you find rho upon epsilon naught, If you do this way, then always keep a caution of Dirac delta function. Usually what happens, students miss this particular thing. Don't miss this particular thing. Keep a caution of Dirac delta function. So my advice would be, try to do this. E vector dot ds vector, integrate it over this spherical, just take a sphere of radius capital R. Sorry, just take a sphere of radius, just give me a minute. If I'm saying take a sphere of radius capital R, this is okay, and electric field in the space is given to be equals to k r square r cap. So okay, so if I do that way, if I want to find what is the flux linked through it, so this is ds vector. Ds vector would be what? It would be equals to capital R square sine theta d theta d phi r cap. So if I want to find E vector dot ds vector, this integration over this particular sphere of radius r, and the surface is denoted by s, then this is equal to integration k r square. And what would be r cap? You can write simply r cap here, dot r square sine theta d theta d phi, and again an r cap here. So r cap dot r cap becomes 1, and this is equals to what? This is equals to summation q upon epsilon naught. The net charge enclosed within this surface S is equal to summation q divided by epsilon naught. So net charge enclosed summation q is equals to what? It is equals to epsilon naught, and this k is not this 1 upon 4 pi epsilon naught. This is simply some different k. This would be r raised to power 4, and this sine theta d theta d phi integration would give you 4 pi. So answer would be this. Is that clear? Now what is the problem with del dot E vector? Now what would you do? I know. So if you are going to do this del dot V vector, if you are trying to do with del dot V vector, what is del dot V vector? This is 1 upon r square del by del r of r square into Vr. This is how you have to do. And if you are doing this, then again you are missing the contribution at, you are missing the contribution at the origin. So for all these problems, please refer to the electrostatics lecture that I have given to you. So if you just see that lecture, I have circumvented all these kind of problems. You'll be able to understand what I want to say. So just go through today, just one of the homeworks that I'm giving to you, just go through the electrostatics lecture. I think Coulomb's law lecture you'll find I have discussed all these things in detail. But my advice at first would be, whenever you have, because why I'm saying this, see, let me come back to the problem. Why I'm saying this, see, if I'm writing del dot E vector, so it is equals to what? It is equals to del dot K R square R cap, right? Or I can write it as del dot K R cube R cap upon, or you can write R ki power 4 this way. Now if you are doing del dot something, so if I am doing del dot u times v vector, it is equals to what? It is equals to grad of u dot v vector. This is vector identity, just remember this, plus u times del dot v vector. And if I am writing del dot v vector, here v vector is what? Here v vector is r cap upon r square. Now this will give you a Dirac delta function. This will give you a Dirac delta function, because if you write this as u, if you write this as u, and if you write this as v vector, just understand, if you apply this property, then del dot v vector would be r cap upon del dot v vector would be del dot r cap upon r square. So what happens? Usually students miss this particular thing, and they directly apply this particular formula, and then you are missing the contribution at origin, and then you are going to get a wrong answer in the exam. So better way is, whenever you have this electric field, because electric field somehow is going to be accompanied by some r cap upon r square. However, this question was that I gave you was like k r square. If you just divide it by r square and multiply, this would be k r ki power 4 of r cap. Is that clear or not clear? So better way would be this. If you really want to go through this way, then don't use this formula, because the time you are going to use this formula, you're going to miss the contribution at origin. Then what you have to do, divide this r cap by r square, multiply by r square, k r ki power 4 become u, and this r cap on r square would give you the contribution at the center. Is that clear? I think this is clear. Please go through the lectures on electrostatics, because otherwise I will divert into electrostatics. That is why I'm not doing this. Please go into the lectures of electrostatics. I've already done them. And if you have any problem, please let me know. I'm just giving you a hint here. Just giving you a hint. Okay, so this is something that you may miss. Now let us evaluate one or two more integrals, and then we'll conclude the class. Okay, so another integral that I want you to evaluate is Dirac r square plus 2 Dirac, not Dirac, this is del dot r cap upon r square. This is how it is given in the book. So you know that this particular thing I can write it as 4 pi Dirac of r. So instead of writing this, I will write it as integration over volume V. This is volume V is of the volume of the sphere. Sphere of volume V centered at origin. So this is what I am giving. Now, if I am talking of a sphere of volume V centered at origin, then this particular thing will give me 4 pi Dirac cube of r. This is simply r square plus 2 into 4 pi Dirac cube r d tau, and this is what here where it becomes 0. It becomes 0 at r equal to 0. Just place r equal to 0 here, so you will get 2 into 4 pi, which is simply equals to what, 8 pi. I hope it is clear. So these are some very basic properties that you should remember with regards to Dirac Delta function. Okay, please let me know if you've understood entire thing in the lecture. Okay, so this concludes our lecture for today. I hope to meet you in the next lecture on infinite series in 10 minutes or so, and then we will move ahead. Tomorrow probably we will start with some different concept or a few problems with Dirac Delta function only, but otherwise I'll start with a new concept like probably matrices or linear vector spaces or anything like. First, let me just build up on mathematical preliminaries, and once I'm done with this, then we will move on to our this thing. Quantum mechanics. Okay. I hope it is clear. So I hope to meet you in the next lecture on infinite series. Just 5 minutes after this, you will have this lecture. Okay. So I hope you will join me there. Till then, take care.